Okay, so welcome to class number 20 of transport phenomena in mesoscopic and nanoscopic systems. So last day we were discussing about the electron-electron correlation function Gn, which basically reads as G sigma in G dagger, where sigma in is basically the in scattering function, and this is basically equal to gamma 1 f1 plus gamma 2 f2. Okay, and this is equal to, if we put this expression for sigma in over here, what we basically get is a1 f1 plus a2 f2, a1 f1 plus a2 f2. Okay, now if f1 is equal to f2, equals to f0, so this is the equilibrium condition basically. In that case we have Gn is equal to a1 plus a2 f0, which is equal to the spectral function a times f0. So this basically tells us that the spectral function a basically has two components, a1 and a2, and a1 is basically equal to G gamma 1 G dagger, a2 is basically equal to G gamma 2 G dagger. So this is the contribution to the overall spectral function or the density of states, because the diagonal elements of the spectral function gives you the density of states by contact 1, and this is basically the contribution to the spectral function by the second contact, so by contact 2. Okay, so now from here let us discuss about the inflow and outflow problem, because in electronics or in electrical engineering, that is what matters. Systems are rarely in equilibrium and we are mainly concerned about the current flow through a device. So it is important to understand, or it is important to derive the equations for the inflow and outflow. Okay, so to make this case simple, we will just assume that the system just has one contact and derive the equation for a one contact system, because directly going into the two contact system is mathematically more rigorous and we don't want to drag those things here. So what I will do is I will just intuitively show the current equations for the one contact system, and since that equation is valid for the one contact system, it should also be valid in general for two contact system or three contact system or whatever, four contact systems also, right? So let us assume a one contact system. So we have this a single contact. So we have this contact and system here, and the system is coupled to the contact via this matrix or this function gamma, and similarly the contact is coupled to the system via this matrix gamma dagger over here, and we just write the Schrodinger's equation, the time independent Schrodinger's equation for this system. So we have E so we'll just write the complete equation first and then we split it up. So we have EI minus H and minus gamma, and then minus gamma dagger EIR minus HR, and then psi here, where psi is basically the wave function of the system, and we denote the wave function inside this contact by phi. So phi, we have a eta as well here, so this is plus I eta. So plus I eta over here, where eta is a very small matrix, or the identity matrix multiplied by a very small quantity, infinitesimally small quantity. We have discussed this before, so I am not going deep into it again. And here this is equal to 0, and then here we have this source term SR over here. Okay, and just as before, this phi is equal to phi r. So phi r is the wave function of the isolated contact, and now since the contact is basically coupled with the channel, so we have another term here which is the part of the wave function that scatters from the system into the contact. So this is phi r plus x over here. Okay, so x is this is basically scattered from the channel into the contact. So we have discussed this before, and phi r is basically the wave function inside the isolated channel. And then we can actually take a few terms towards the left and write it in a different format. So we can write it as E psi phi is equal to H gamma dagger HR minus I eta psi phi plus the source term SR. Okay. Now, due to the time dependent Schrodinger's equation, this part and hence this entire part must also be equal to I h bar d dt of psi phi. Okay. Now, let us ask ourselves this question, that what is the current flow out of the system or into this system over here. Okay, this is a one contact system. So here, how do we measure the current flow? So current flow is basically the rate at which charge flows into the system, or the rate at which charge flows out of the system. Of course, the first case is equal to the negative of the second case. Okay, so how do we measure the charge inside this system, the total charge? So it is just the square of the mod of the wave function. So the total charge inside the system this is equal to, so total charge inside the system, not inside the contact. So system is just what is coupled to the contact. Okay, so the total charge inside the system is equal to mod of psi square, and this can also be written as psi dagger psi. Okay, now the rate at which this total charge inside the system changes with time is equal to the current flow. Okay, so we will assume that the current flow is positive if the charge enters inside the system, that is charge inside the system increases with time, and we will assume that the current flow is negative if charge gets out of the system, that is the charge inside the system decreases with time. Okay, so the current therefore into the system from the contact is equal to d dt of the total charge inside the system, the rate at which the charge inside the system changes with time. So d dt of psi dagger psi. So this is nothing but this is equal to d psi dagger dt psi plus psi dagger d psi dt. Okay. Now to proceed from here, that is to go further beyond this term d psi dagger dt and d psi dt over here, what we do is we basically use this equation d psi dt, and we use this left hand side, that is this part of our equation. Okay, so we just replace it here. So this is equal to 1 by I h bar, and this is equal to h psi dagger actually, or psi dagger h dagger to be more precise, because this let me write it here, AB dagger, this is equal to B dagger A dagger. Okay, it's not difficult to prove, it just comes from linear algebra. So if you are not convinced of this formula, just go and look into some basic engineering mathematics book. Okay, so this is basically equal to psi dagger h dagger plus phi dagger tau dagger. Now and this is multiplied by psi, so this part is basically, so let me write it like this. Now because this Hamiltonian is actually Hermitian, so h dagger is equal to h, so I basically remove this dagger over here, and then the second part is equal to psi dagger h psi plus sorry, this is equal to phi dagger tau dagger, not tau dagger phi dagger, so this is phi dagger tau dagger over here plus tau phi bracket close. Now another thing that we need to keep in mind is that if we basically take the complex conjugate of both this side, complex conjugate transpose, that is of this side and of this side over here, a minus sign would creep in, because this I would basically become minus I. So this equation, if I take the complex conjugate, this equation would look something like minus IH, because I becomes minus H, I becomes minus I now, and then we have this dagger sign over here, and then we have this dagger sign over here, and here we have this dagger here, this dagger sign goes away, then we have a dagger here, and then this one basically becomes positive, and because of this I over here. Okay, so because of this I transforming into minus I, we basically should have a negative sign over here. So I forgot to add that, let us add this negative term over here. Now we note that this term over here, let me just point it out, this term multiplied by this psi over here and this term are same, and they cancel out each other. So we are basically left with only two terms, which is 1 by I h bar phi dagger psi dagger tau phi minus phi dagger tau dagger psi. Okay, now we note that this phi again, this consists of two terms. One is the wave function of the isolated contact, which is kind of the property of the contact itself, and the other part is basically the scattered wave function from the channel or the system into the contact. So phi is equal to phi r plus x. So we put this equation for phi in here, and what we basically end up getting is 1 by I h bar psi dagger tau phi r minus phi r dagger tau dagger psi, and then due to the scatter part we get a second term which is minus 1 by I h bar x dagger tau dagger psi, let me write x dagger tau dagger psi minus psi dagger tau x. Okay, now this part basically, this entire part basically depends on the wave function inside the channel or the system and the original wave function of the isolated contact. Okay, so this part must be equivalent to the inflow term, because the wave function of the isolated contact are basically entering into the channel. So since it depends on the wave function of the isolated contact, this must be equal to the inflow term. I am not giving a rigorous mathematical reason here, but I hope this intuitive reason is sufficient for you to understand. And this part basically depends on the wave function that is scattered from the contact into the channel, that is scattered from the channel into the contact or from the system into the contact, and that part of the wave function is basically this x. Okay, so since it depends on the part of the wave function that is scattered from the system or the channel into the contact, this must be the outflow term. Okay, so let me write it in a different way. The total current that enters from the contact into the channel is equal to the net current that enters from the contact into the channel, which is I in, minus the current that gets out of the channel into the contact, which is I out, and this is basically, I write again, is equal to 1 by I h bar psi dagger tau phi r minus phi r dagger tau dagger psi minus 1 by I h bar x dagger tau x dagger tau dagger psi, let me write it here, x dagger tau dagger psi minus psi dagger tau x. Okay, and this total part is precisely the inflow term, and this total part is the outflow term. Now let us go into a little bit more detail from here. So the current that flows into the contact, the current that flows into the system or the channel from the contact is given by I in, which is 1 by I h bar psi dagger tau phi r minus phi r dagger tau dagger psi. Now we know that the psi is equal to g times s, where g is the Green's function of the channel and s is basically the source term, and s is equal to tau phi r. Okay, so here this would hence become 1 by I h bar. Then this psi dagger, this basically comes equal to S dagger G dagger, and then this tau phi r, this is basically equal to S, so we have S over here, and then this is basically equal to minus S dagger G S. Okay, so this again basically becomes equal to 1 by I h bar S dagger G dagger minus G into times S. Okay, so equal to minus I by H. So let us not write the minus I here, but minus 1 by H bar S dagger I G dagger minus G S, and then we can pull this, so this is an I here, so now we can pull this minus sign inside this bracket over here, so this basically becomes G minus G dagger, and then this part we know is equal to the spectral function A, so this basically becomes I by H bar S dagger A S. Okay, sorry, not I, because I have put this I over here, so we don't have an I here, so 1 by H bar. Now note that this part is basically a number, although S is a matrix, this A is a matrix and S dagger is a matrix, but this total part is a number. Why? Because this S is basically, this one is a column vector, okay, and this is a square matrix. So a square matrix, when it multiplies a column vector, we get a again we get a column vector, and this is basically a row vector. Okay, so this is a square matrix, this is again a row vector, so a row vector multiplied by this column vector, this total is a column vector, so a row vector multiplied by this column vector, this becomes a number basically. Okay, so this is also, we can write it as also equal to trace of so let me write it in different way, so this is equal to 1 by H bar trace of S dagger A S. Okay, now since this total part is a number, so this number is equal to its trace, so it's like a one element matrix, so this number is equal to its trace basically. Trace is basically the sum of the diagonal elements of a matrix, so if a number, in case of a number, we can treat it as a 1 cross 1 matrix, and this number is equal to its trace. Okay, now we have this property that trace, this again comes from linear algebra, and it is taught in the first year of engineering, that trace ABC is equal to trace CAB. Okay, or let us say a trace of AB is equal to trace of BA. Trace of AB is equal to trace of BA. So we basically apply this property over here, and we write it this as equal to 1 by H bar trace of S is dagger A. Now note that this is not important to do all these things, but why we are doing this is to get a compact expression, because we actually, in reality, we do not know what this matrix S are. We of course, and it's actually difficult to compute actually. We want a compact expression through which we can actually compute things directly in a computer. Okay, and so S is equal to tau phi r. and this phi r is actually not known to us. Now to know phi r, we have to solve for the eigenstates of the contact, which again is a tedious job and computationally heavy job. So we do not want to go into all those detailed computations, but we want an expression through which, given the property of the channel or the system and given the contact to channel coupling, we can basically find out the current voltage properties or the non-equilibrium properties of the device. Okay, so this matrix, this coupling matrix is basically known to us. It is basically how the contact and the channel are coupled to each other. But this matrix psi r or this vector psi r is basically not known to us. So it's basically difficult if we keep this equation in this form over here or the previous form. So we basically want to break it down further. So this basically then becomes equal to 1 by h bar trace of S is equal to tau phi r and S dagger is equal to phi r dagger tau times A. Now we do not know what this row vector phi r is, because this is the kind of eigenstate of the contact, but we kind of have an idea that what kind of matrix this would be, because this basically depends on the statistical properties of the contact. Now from our previous class, we know that this matrix phi r dagger, this can be actually written as the integral of dE by 2 pi, then f0 E minus mu ar E. Okay, now why we are using this equilibrium Fermi function f0 but not the non-equilibrium Fermi functions f1 and f2 is because this wave function phi r, this is actually the wave function for the isolated contact. So when the contact is isolated, of course things would depend on the equilibrium properties of the system. Okay, the contact is a macroscopic body, so things here depend on the equilibrium properties of the system itself. Okay, so this is equal to dE by 2 pi f0 E minus mu ar, and remember that this is the spectral function of the contact, and this is basically a matrix actually. Okay, so therefore S dagger, this is equal to tau phi r. We have another dagger over here, tau phi r dagger tau dagger, which is equal to integral of dE divided by 2 pi let me write it different way, f0 E minus mu, and then we write this tau matrix here and ar tau dagger. Now remember that this is equal to the gamma matrix, so we write this entire thing as, we just delete this part, so we write this entire thing as equal to integral of dE divided by 2 pi f0 E minus mu and then gamma. Okay, so we write this, we just ignore the matrix notation, but just remember that this one and this one are basically matrices, or it can also be functions, but here since we are trying to see the numerical perspective, these two would be basically matrices. Okay, so the overall this inflow is basically equal to In. So let me use a different page. So the inflow is equal to I in, which is basically equal to 1 by h bar trace of S dagger A, and this is basically equal to 1 by h bar trace of gamma A. We also have this integral sign over here, so E minus mu, and then trace of gamma A, and this is basically our compact equation for this inflow. So gamma matrix we can know directly from the contact to device coupling, and this spectral function of the system is also known because we know the Green's function of the system or the channel. So this entire matrix is basically known to us. So we basically have expressed the current that flows from the contact into the system in terms of parameters or functions which are basically known to us. Now let us look at the outflow term. Now in this case, this term x and x dagger, which are basically this term over here and this term over here, these two are basically unknown to us, and we need to find a compact expression by bypassing these terms. So we basically know that this x is basically this is a part of the wave function that is scattered into the contact from the channel, and this is basically equal to gr, where gr is the Green's function of the reservoir, not of the channel of the system. So gr is the Green's function of the contact. Okay, tau dagger psi. So this was the original expression. So here it is x dagger over here. So we have it as 1 by I h bar, and then psi tau. This would be psi dagger actually, psi tau and gr dagger, tau dagger psi minus. So this is, there is a dagger over here, psi dagger tau gr tau dagger psi. Okay, so let me draw a box over here, and this is equal to 1 by I h bar. Now what is this term over here? What is this term? So this, if you remember, is sigma dagger. So sigma was basically equal to tau gr tau dagger, if you remember. So this part is precisely equal to sigma dagger. So psi dagger sigma dagger psi minus psi dagger sigma psi. So this is again I by h bar psi dagger sigma minus sigma dagger psi. Okay. Now what is this part? This I times this sorry, what is this part? This I times this sigma minus sigma dagger. This part, if you remember, this is equal to gamma. So this basically becomes equal to 1 by h bar psi dagger gamma psi. Okay. Now this is equal to 1 by h bar, because this is again a number, so this is equal to its trace. So 1 by h bar trace of psi dagger gamma psi. So by the same property as before, this becomes equal to trace of psi dagger times gamma. Okay, so note that psi is basically the wave function inside the channel. As per what we have discussed before, this psi dagger, this can basically be written as integral of dE by 2 pi Gn, where Gn is the electron-electron correlation function. Okay, so this outflow basically becomes equal to I out equals to 1 by h bar integral of dE by 2 pi trace of gamma times gn or gn times gamma. This basically both are the same. So this is basically our current flow from the channel or the system into the contact. Okay. So the total current flow is therefore given by I equals to I in minus I out, which is equal to 1 by h bar integral of dE by 2 pi and then multiplied by gamma A times F0. Actually we have this trace over here, so trace of gamma A, and F0 is basically again a number, so we can include it inside the brackets, minus trace of gamma times Gn. Okay, this has a very nice significance. Let me discuss the intuitive aspect of this equation. So gamma is basically related to the rate at which electrons flow from the contact into the channel or from the channel into the contact. This we have basically discussed earlier, that gamma is basically related to the imaginary part of the matrix sigma, and it is related to the rate at which electrons can leak from the contact into the channel or from the channel into the contact. Okay. So gamma it basically gives us the rate at which electrons can flow between the channel and the contact. Now A is basically the spectral function, and this we can basically measure the density of states from this function. Density of states of the system, that is system of the channel. Okay. So and F0 is basically the Fermi function inside the contact. So the total inflow of the electrons from the contact into the channel, this is equal to the rate at which electrons can flow from the contact into the channel multiplied by the density of states. Okay, if there are no density of states inside the channel, then electrons cannot flow from the contact to the channel. So the rate at which electrons can flow from the contact to the channel multiplied by the density of states inside the channel multiplied by a factor which determines that if that energy state inside the contact is filled or empty. So if the state inside the contact is empty, then no electrons would flow at that energy from the contact into the channel. Okay. So this is the classical interpretation of this expression. And similarly, the rate of outflow of the electrons from the channel into the contact, which is this part, is equal to the rate at which electrons can flow from the channel into the contact, which is the coupling, times the occupancy of electrons inside the channel. So if there are electrons present inside the channel, then only the electrons can flow out of the channel into the contact. So this electron-electron correlation function, the diagonal elements, basically give us that whether electrons inside the channel are present or not. Okay. So the rate at which electrons can flow or can leak into the contact times the occupancy of electrons inside the channel. Okay, this basically measures the outflow of the electrons. So that is the classical interpretation of this formula over here, formula or expression over here. So let us do up to here today. This part is complicated and mathematically rigorous, so takes some time to sink this part inside your head. So we'll continue from here on the next day.